Welcome everyone. Thank you for joining us for today's webinar. My name is Reidun and I'm the marketing manager at Aanderaa, and I will also be hosting this session today. Today we are presenting the webinar How do surface wave buoys, acoustic wave measurements and pressure-based wave solutions compare? Presented by Ms. Emily Dorcheville and Mr. Stig Owen. During this live webinar, you will learn about the innovative technology implemented in the SeaGuardII DCP Wave to provide high-quality directional wave measurement and reduce the measurement noise. We will also guide you through some of the applications where this solution can be utilized. Just some practical information before we get started. If you have any questions during the presentation, please type them into the question box in your GoToWebinar control panel. I'll bring them up during Q&A session after the end of the presentation. Now, without further ado, we will turn over to two very excited panelists who will introduce themselves. Please go ahead. Emily, will you like to start?
Yes. Hello, everyone. Thank you, Reidun, for your good presentation. So we are excited to be here today to talk to you about our complete wave solutions. So my name is Emily Dorcheville, and I am the product manager at Aanderaa. I've been working with the company since 2008, and lately I've been working intensively with wave products, especially with the MOTUS wave and the SeaGuardII DCP Wave, which is the new product joining the family. And now, Stig.
Yes, thank you. My name is Stig Owen. I'm the water segment leader in Aanderaa. And also, I've been working with business development for marine transport now since 2013. So I'm one of the youngest guys here. Now I would like to get started with just presenting a few facts about Xylem and who we are. Aanderaa is one of some 30 brands that Xylem is the owner of. In Xylem, we're about 17,000 people spread out around 400 different locations worldwide. Through our corporate citizenship program, Watermark, Xylem employees have volunteered more than 100,000 hours over the last 3 years. Some of the things we have been doing there is educating about key water issues, cleaning up local waterways, and more. Now I would like to talk a little bit about a dramatic weekend off the coast of Norway in late March 2019, as a large cruise ship with more than 1,300 people on board lost all engine power and drifted towards shore in gale winds. 100 meters from shore, its anchor finally catched, and a complete disaster was avoided. During these hectic hours, rescue helicopters were used to evacuating passengers. The waves were too high for launching the life rafts. Launching life rafts in these conditions would be the last option before hitting land. Here we can see how it was for the passengers during these hours.
So this gives you an idea about how much wave means when you sit on the boat.
There. It's not a pleasant time for the passengers, and it lasted for quite a few hours. During this event, there was a MOTUS buoy operating in an area not so far away. It is expected that the conditions in both these areas are pretty much the same. Large waves were experienced with a maximum wave height of 18.3 meters and a significant wave height of 10 meters. So the conditions was quite tough. Comparing these two areas, like I said in the beginning here, it's pretty much the same. What is a little bit interesting is that one of the navigational marks, the mooring lines broke on that one in that area. but one of our MOTUS buoys actually survived that. But luckily, no lives were lost in the accident.
Yes. Thank you, Stig. Yeah, that's quite impressive, and that shows the importance of getting a better understanding of the wave conditions. So today we will especially focus on presenting the free Aanderaa wave solutions. What are the advantages with those solutions? Then we will talk a little bit more into details about the wave functionality for the SeaGuardII DCP Wave. And we will also introduce the adaptive pulse technology, which is an innovative solution that we have implemented for the first time in this instrument. And it aims at optimizing the wave measurement and also extend the wave range. Also, the SeaGuardII DCP Wave has been intensively tested during several months and compared with the MOTUS Wave Buoy, as well as the Data World Waverider. And this SeaGuardII DCP was also equipped with a pressure-based wave sensor. So we will present the data from this test. And then Stig will conclude by advising you on which solution is the best to use according to your application. So the three different ways to measure waves. To measure waves, when you want to measure waves using a buoy platform, you are depending on the ability of the buoy to follow the surface displacement. And this is something that is usually done using a dedicated wave buoy. So it's a small spherical buoy. But it has the disadvantage of offering little flexibility, and it will also provide only few parameters with limited telemetry options. So the other option is to use larger buoys, like this type of buoy, navigational buoys. So they will provide longer deployment and the possibility for monitoring additional parameters. You can get a complete picture of the environmental conditions. But the challenges with this buoy is to measure wave accurately because of their size and their ability to follow the surface displacement. And this is what Aanderaa has been solving with the MOTUS wave sensor. So the MOTUS wave buoy provides a full set of directional wave parameters with the flexibility of a mid-ocean buoy. It also provides you an extended wave insight with the separation between swell and wind, and you can also get frequency or and time domain-based wave analysis. This technology has been tested and field proven during several years against the Data World Waverider. So I will say a few words about that. Now, if we think about the bottom-mounted solution, so the advantage with this type of solution is that they are not seen from the surface, and then they won't disturb the navigation. Here, if you are working in a channel or in a place with a lot of navigation. However, it could be challenging to maintain the system. Sometimes you have to send some divers, and it can be quite complicated. And also, if you need the longer cables, it can be an expensive solution. But it also provides a lot of advantages too. If you think about the SeaGuardII DCP Wave, you can get a complete picture of the environmental conditions here, because you can measure directional wave, the currents, and you can also easily integrate water quality in one instrument. Also, thanks to this new technology, the adaptive pulse that I will talk a little bit more about, we optimize the wave measurement accuracy. And also, that's a solution that we have been testing during several months this winter. So we will present the result from this. But here we match the industry standard. And then we have the third alternative, which is a pressure-based sensor. This will provide only non-directional wave measurements, but the advantage is that it is a low-cost alternative. It is a very small sensor, and it is very robust, easy to use, to deploy, and to integrate into systems. It is based on highly reliable technology. And also it is based on the smart sensor technology. So all wave statistics are processed and calculated into the sensor. So directly engineering value will be given out. So this is an overview of the parameters that will be provided by the 3 different solutions. If you look here in the middle, the MOTUS. So the MOTUS, it will provide up to 20 wave parameters. So you can select which parameters you want to be provided by the sensor. We have the swell and wind separation. The MOTUS sensor will provide you the complete wave spectra, including the first 5 Fourier coefficients. And it will provide you with the time and frequency-based analysis. So when we talk about the time and frequency-based analysis, here we refer to 2 different ways of characterizing the same wave signal. When we talk about the time domain-based analysis, we look at the surface variation in time, also referred to as the heave time series. So this is this parameter here. And we also give this parameter, the H1 third, which is a time-based analysis parameter. So to determine this value, we select 1/3 of the highest wave in the measurement interval, and we average them. Here we also give out the maximum wave height, which provide the highest wave in the interval. And this is very valuable in case you want to evaluate the worst case scenario. If you're interested in structure design, for example, and it can also be useful if you are looking at rogue waves. When we talk about the frequency-based analysis, it describes the wave energy as a function of the frequency. So if you look at the SeaGuardII DCP Wave, here it will provide you directional wave information. It will provide the wave spectra together with the first 5 Fourier coefficients. It will provide a frequency analysis. Here we don't get any time analysis, only frequency. And the SeaGuardII DCP Wave, and it will be also the same thing for the wave pressure sensor. It has some limitation because it's an instrument deployed in the water. And it will be limited in the detection of the high frequency bandwidth or the shorter waves because they are dependent on the deployment depth. I will explain that into more details later on in the presentation. But if you look at the wave and tight pressure sensor, it will provide non-directional wave spectrum. It will provide time and frequency-based analysis. And it is also has some limitation due to this deployment depth. So now if we talk about the SeaGuardII DCP Wave, the SeaGuardII DCP Wave differs from the other acoustic solution in 3 different ways. First it provides waves and currents, but one thing that Aanderaa has been always strong on is the possibility to integrate water quality sensors in one instrument. So the SeaGuardII DCP Wave provides you a robust unit that will measure a wide range of parameters. It is also based on the adaptive pulse technology that will optimize the wave measurement accuracy. So this technology will automatically switch between different acoustic modes to get the best result depending on the conditions. And the solution has been intensively tested, so we have field proven and validated data. So if we look at the SeaGuardII DCP Wave advantages, first, you can use it as a real-time instrument or as a self-recording because of all the current and wave parameters are on board processed. You can measure wave and currents independently with a flexible setup. Like for example, when you measure the currents, you can refer the columns either to the instrument or to the surface. So when you refer the columns to the surface, when you will have some variation with the surface, like the tide, the column also will move together with the surface. And when you refer to the instrument, it will always keep a fixed distance to the instrument. One of the things, when we also measure the waves, we will provide current from the free cells closer to the surface. We also have the ability to measure a wide range of parameters using the Aanderaa plug-and-play smart sensor, which includes temperature, pressure, conductivity, oxygen, and the wave and tide sensor. And we also have the possibility for easy integration of third-party sensors, so serial and analog. We have 2 serial inputs and 4 analog inputs. So you can integrate different types of sensors depending on the application, but it could be to measure pH, turbidity, and we also had some application where we are using the EXO from YSI. We also have real-time communication, so you can have a 2-way communications. It means that you can reconfigure your instrument remotely and like get your data remotely as well. We have support for AIS and Goose as well. And in terms of real-time transmission, you can define your recording interval and transmission interval independently, which means that you can, for example, record every 10 minutes, but transmit data only every hour. Also, thanks to this wave and tide pressure-based sensor that is plug and play onto the SeaGuardII DCP, we can get redundant wave measurements that could be very useful for quality assurance. And the SeaGuardII DCP Wave can sample at 2 Hz or 4 Hz, so this is configurable. 4 Hz will provide higher accuracy. But the advantage with the 2 Hz, it will be less power consuming, so it will depend a little bit on your application. And then you can set up the integration time from 5 minutes to 30 minutes. So how do we measure the waves using an acoustic profiler? So when you use a Doppler current profiler, it's measure the particle speed based on the Doppler principle. So when the waves are passing by a location, they induce orbital velocity. So they induce some particle movement in an orbit, orbital movement. And if you look on the illustration here, you can see that this orbital velocity, they will decrease while the depth increases. And at a depth called here the wave base, the orbital orbits will become so small that the movement is negligible. And then you have hardly any motion existing under this wave base. So this wave base is equal to 1/2 of the wavelength, which means that the wavelength will control the depth of this wave base. So the longer the wave, the deeper the wave base here is, and on the opposite, the shorter waves will attenuate more rapidly. So if you look a little bit closer at this position here, if we want to measure the shorter wavelengths, it means that the cell where we want to measure the orbital velocity should be as close to the surface as possible. Otherwise, we risk to not detect the orbital velocity. And one of the thing with when you use a current profiler is that you have a contaminated zone, which is about 10% of the deployment depth. So if you deploy your instrument at 40 meters, it represents about 4 meters, which means that the first cell that you will be able to measure the orbital velocity will be positioned at 6 meters. So if the wave field is in the short wavelength, which means the high frequency waves, or if the cell where you're measuring is too low under the surface, then the orbital motion will be so low that it might be lower than the safe noise of the measuring system. If you look at this graph here, which is a representation of the energy spectrum according to the frequency, you will see that the spectral energy decays when the frequency increases here. So we can see in blue, it represents the energy measured by the SeaGuardII DCP Wave. So we see that here, the safe noise will be amplified and it will dominate the signal. So for this reason, we need to find a solution to keep the safe noise of the acoustic measurement system at a minimum in the higher frequency. And this is the purpose of this newly developed pulse adaptive technology. So while the instrument is working in broadband, because we send an acoustic pulse, and it is based on the broadband technology. So in this broadband technology, we transmit two subpulses. And the lag, or the spacing in time between the start of each subpulse, is a configurable parameter that will influence the overall measurement noise, or in other words, the uncertainty. So the adaptive pulse technology consists of modifying this broadband lag and reduce the noise in the higher frequency. So here we'll be switching between three different modes, 2 broadband and 1 narrowband, that will optimize the signal to noise ratio. So I won't go further into detail about this technology, but if you are interested, it's going to be soon published and available on our website. But basically, if you are in a low sea state condition, so it's about less than 2.2 meters, then we will use broadband mode called 0, also referred to as a low noise mode, that will use a relatively long lag pulse and will keep the safe noise of the sensor very low. Then when we come in a medium-sized wave condition, which is about between 2.2 and 4 meter wave height, we will switch to a broadband mode 1. And then when we come in more extreme wave situation, we will switch to a third option, which is a narrowband solution. And this is at around 4 meter wave height. So the advantage here is that you don't have any user interaction. This is all done automatically. And it will also optimize the wave measurements by reducing the noise and also providing better accuracy and extend the wave height range. So we'll be able to also measure the smaller wave, the shorter waves. So here is a graph to illustrate a little bit about this principle. This is some data that has been collected. So in blue, it is from the SeaGuardII DCP. So this is the significant wave height. In red, it is with the MOTUS wave sensor. In yellow, it is from the data well Waverider. So you look at the wave according to time. And in purple, it's the broadband switch. So at the beginning of the interval, we see that we have very small wave, less than 2 meters. So here we are working in broadband mode 0. So in this case, we need to have to minimize the signal to noise ratio. So we are working in broadband 0. Then when we come into a situation with a little bit higher wave, the instruments here we switch to the broadband mode 1. So during this period where we have a little bit more sea, a little bit more agitated sea, we are working in broadband mode 1. And then around the 10th of February, we see that we have a little bit higher waves, over 4 meters. So we see when the waves are more than 4 meters, then we will go to a narrowband mode. So all these measurements are done in narrowband. And then again, when the CR conditions are getting lower, when we go down to less than 2 meters, we will switch to broadband mode 1 again. And then you can see in this period, we are at the edge of this broadband 1 and broadband 0, so the instrument will switch, trying to always optimize the noise. So it will look at the best solutions to get the best measurements. So that's basically about the adaptive pulse technology. So when I talk to you about the MOTUS solution, here we have no limitation in the frequency band. And I told you that with the pressure-based wave-based sensor and the SeaGuardII DCP Wave, we will have some limitation due to the depth deployment. And this is due to this wave attenuation. So when you deploy the instrument at 40-meter depth, the instrument will have some difficulties to detect the high-frequency wave. So when we deploy the instrument at 40 meters, we'll be able to measure all these waves, but it will stop at 0.2 Hertz. And the deeper the instrument will be, the bigger the wave will have to be measured. But in the opposite, if the instrument is shallower, then we will be able to extend the frequency limit. And you see here it's different in the wave height, and it's a different cutoff frequency for the direction as well. So the field results, we have been comparing the 4 different methods to measure waves. So we have deployed the SeaGuardII DCP Wave in the west coast of Norway. Here you can see at this location. So the SeaGuardII DCP Wave provides acoustic wave, and it has also been equipped with a pressure wave-based sensor for non-directional wave measurement. So you can see here it's deployed here, and then we have the 2 buoys, one MOTUS wave buoy deployed here, which is equipped with the Doppler current profiler downward looking, and we have the data well Waverider buoy located a little bit further south. That is also used as a reference. So just a few words about the MOTUS features. When we developed the MOTUS sensor, we wanted to develop a sensor able to be mounted on any type of buoy, including non-ideal buoy. By that, we mean buoys that are not specifically designed to follow the water surface displacement. So we spend a dedicated amount of time of our R&D efforts to optimize the performances of the sensor in order to reduce the power consumption. So now we have a power consumption that is less than 125 milliwatts at 12 volts. So this is the wave sensor with the lowest power consumption available on the market. We also implemented some compensation for the buoy response, because the MOTUS is meant to be used on different types of buoys, and the buoys will respond differently on the wave conditions, and also it will be influenced by the mooring. So here we have the possibility to compensate for that. We also have implemented the off-center compensation, because it is not always possible to position the sensor in the buoy center of gravity. So we need to compensate for that. We see that from the test we have done, if you have a 50 centimeter offset, it can induce error up to 15%. The advantage with the MOTUS buoy is that you have a flexible configuration. You can easily integrate meteorological station. You can have different head-to-navigation solutions. We have real-time data delivery. You have wave measurement. You also have different water quality sensor possibilities, telemetry options, and we have a wide range of current measurements. You have single point current sensor and profilers. So the advantage here is that you have a flexible configuration, and you can customize your buoy according to your application. One of the difficulties when you are working with a buoy is magnetism, because both the current sensor and the MOTUS sensor, they are using a compass, and the compass is can be disturbed by the magnetic interference. So if you are using a buoy with a magnetic disturbance, you have the possibility to use an external compass, and it will help you to correct for these disturbances. So this compass can be connected to the data logger of the system, but it can also be directly connected to the MOTUS sensor. And one of the advantages is that Xylem can provide a complete solution from one vendor. So in few words, the MOTUS sensor offers data that have been validated to our references. We have some MOTUS buoys that have been deployed during several years, compared with the data well, and provided excellent data. It provides the best accuracy for wave and current measurement from a full scalable navigational buoy. And the added value with the MOTUS buoy is the ability to deliver multi-parameter data, its flexibility and reliability, and also competitive price. Few words about the wave pressure-based sensor. So this graph represents the drift of the different versions of the Aanderaa pressure sensor. So it's an evolution after several days. We deployed the sensor in the sea, and we can see, so it's numbers of days, 200 days, 400 days, up to 1,200 days. And then we recalibrate them at the factory and check also the drift of the sensor. So here we can see that our pressure sensor have had very little drift during this deployment, and the given specifications are far better than the expectations. So this sensor is very small, and it's easy to deploy. It's a very robust sensor and easy to integrate in different types of applications. It has provide very high accuracy solutions, data, and it will also automatically calculate the wave statistics. So this is the result from the test we have done at the Karmøy site. So this first graph, it shows the comparison between the MOTUS sensor compared with the wave pressure sensor. So here we see we have a little offset, and this is due to the MOTUS wave and the wave pressure sensor that are not located at the same position. But we see that we have a very good correlation between the two solutions. So this graph, it shows the significant wave height compared between MOTUS and the Waverider. So here we see that we have excellent comparison. This one shows the comparison between the Waverider compared with the SeaGuardII DCP Wave. So here again, they are not positioned at the same position, at the same location. So we can see that we have a little offset, but it's giving a very good correlation. And this latest graph, it gives comparison between the pressure-based wave sensor and the SeaGuardII DCP Wave. So both sensors are located at the same location, and we can see here that we have excellent correlation. So the four different measurements that we get compare very well in terms of the significant wave height calculation. And if we look at the energy spectra, this graph on the left, it represents the wave peak direction. So it's the comparison between the SeaGuardII DCP and the data Waverider. So here again, during this interval, we have very good correlation between the two measurements. And here we can see the energy spectra depending on the frequency. And then we can see here that the SeaGuardII DCP Wave, which is the red line, it stops at 0.3 here, but we can see that we also have a very good correlation between the two measurements. If we look here at the energy spectra from the SeaGuardII DCP Wave compared with the Waverider, so on the top, we look at the energy spectra compared to the frequency. Oh, no, sorry, on the left here is the comparison between the Waverider and the SeaGuardII DCP Wave. So here we see that we have very good correlation between the two measurement means. And then on the right here is a representation of the directional spectra. So again, we have a very good correlation. So now I pass the hand on to Stig.
Yes, so we have just put up a slide here with an overview of where the three different methods of measuring fits in. As you can see from this overview, the SeaGuardII DCP Wave can be installed a little deeper than the wave and tide sensor. What the users need to consider is the waves in the area. The longer the waves, the shorter the waves, the more shallow the instrument or sensors needs to be installed. For the MOTUS buoy, it depends more on the tide level if you are in very shallow installations. We need to have water underneath the buoy to be able to measure on it. If it stands on the bottom, then we cannot measure anything, basically. I would say that the Aanderaa instrument fits in most environments, that being for ports and harbor, coastal monitoring system, scientific research, and more. If we look a little bit on the benefits, like Emily pointed out, the wave and tide sensor is robust and easy to install sensor. One of the other things is that if you just want to measure the wave and the tide, then you can easily just use that. It's a low-cost alternative for that. You can extend that into a bigger system, adding, for instance, single-point current. You can add a weather station to it, and so on. One of the biggest advantages of the SeaGuardII DCP Wave, or I would say not advantages but benefits, is the use of the smart sensor, the plug-and-play sensors directly on the instrument. So if you want to measure environmental parameters at the bottom of the ocean with the instrument, you can just plug in extra sensors on it. And then, of course, on the MOTUS buoy, you have the possibility to separate between swell and wind-driven waves, and also to combine the EXO from YSI directly on the buoy itself. So I tried to look a little bit on some application of where the SeaGuardII DCP Wave would fit in. This being a new instrument, we haven't sold it to any of the customers. Well, actually, we do have sold it already, but it's not installed already. It brings me back to a system we delivered about 15 years ago, right here in Bergen, which was the wavelength system. In 2004, there was a stone carrier called Rockness hit an underwater rock and capsized. 18 people died in that accident. And due to the local conditions in the area, where it's narrow and strong currents, the Norwegian coastal authorities and Aanderaa installed a HIDMET station on the beacon in the ship lane where the ship capsized. In the picture here, you can see the ship is floating upside down. This is very close to Bergen. It's about a 5 minutes drive out. Just going to the next application, which comes to mind, is the Safe Port project in Gdynia, which was also done a few years ago. There we did some field work for more than a year and provided data into a model that was developed to supply ferries entering into the port of Gdynia with wind and current and wave data, and to make sure they have a safe approach into the harbor, because they had some problems there with some ferries hitting the breakwater, getting pushed by the wind and the currents into the breakwater. So that is typical application where the SeaGuardII DCP Wave would fit in. Looking at the next one here is a MOTUS buoy we have delivered. Actually, this is the MOTUS buoy that we saw the screenshot of the data from during the storm and the cruise ship with the problems. What is special about this one is that all the data is sent to a hosted cloud solution. And here at Aanderaa, we do the conversion over to a NetCDF format of the data. It is then forwarded to the Met Institute. They validate the data, and then it goes to the Coastal Administration, and they publish it then on internet. For the pressure-based ones, I was thinking back at the Statoil Kårstø, which now is then Equinor Kårstø. They, in 2013, they upgraded their system also to have wave and tide sensor from Aanderaa in their system. The first system there was installed more than 10 years ago and have been running ever since. Right now it's up for maintenance, but it has been a very successful story. But in 2013 they wanted to add also wave and tide measurements in the area, but also to measure the water temperature at 6 meters depth. So we did the installation directly onto the existing SmartGuard. So we expanded the system, which was already existing, with another sensor.
Okay, thank you, Stig, for your good example of different applications we could use our solution into. So now we have presented how the surface wave solution, acoustic wave and pressure-based compare. The data have been validated through intensive tests over several months and several years for the MOTUS buoys and the pressure wave sensor. We have presented which conditions apply in order to select the right solution for your application and the benefit from each of the three solutions.
There's no need for a dedicated technical department to work with the Aanderaa solution. It does not require high technical understanding of the instrument and the sensors. Right.
And also we have different type of solutions to measure wave, current, and environmental parameters. So that's the benefit of Aanderaa solution. So thank you for listening to us. Now I will pass on to Redin. I think several questions come up during the presentation. So she... Yes, Redin?
Thank you. I see that you have been doing a great job. We have several questions. We will try to answer as many as we can, but I see that due to the time, we will have to you guys will have to get back to many of them with some answers after the webinar. But we will speed up a little bit and start right ahead. I'll go with the first one for you, Emily. While measuring waves, do you also measure currents simultaneously?
So when we measure, so when you configure the instrument, you define when you want to measure currents and when you want to measure waves. So when you measure waves, because you measure the orbital velocity close to the surface, you also have the possibility to get the currents from this measurement. So when we do the wave measurements, we do that in the free cells closer to the surface. So we will also give out the current measurement from those free cells. So yes.
Thank you, Emily. Another one here is, do you supply a post-processing software which allows for display of wave spectra?
So when we use the SeaGuardII DCP, you also have you can get the data in real time. First, we have the GeoView real-time display, which is web-based. But we will also supply the instrument with the Data Studio 3D, which is the post-processing software provided with the instrument, which allows you to visualize and analyze your data. You will also have the possibility to look at the spectrum value, and also the data are provided with some quality flag information. So you also have the possibility to quality check your data using this processing software. Then if you need to further analyze your data, if you are used to process your data in MATLAB or Excel or whatever, it's also possible to export the data using this post-processing software.
Great. Thank you. Another one here is, how big is the contaminated zone?
So yes, we talk a little bit, I refer to the contaminated zone. This is something that is due to the Doppler technology. Because of this side loop contamination, we say that the contaminated zone is about 10% of the deployment depth. So if your instrument is deployed at 30 meters, it will be about 3 meters close to the surface. So in these 3 meters, you will not be able to do any current or wave measurements.
Let me see, there is one more here. When measuring currents, you have an overlap possibility, but is it also possible to space the cells from each other?
So when we measure the currents, we have the possibility to you can define 3 different columns, and these columns you can define the cell size, and you can also have the possibility to overlap the cells, which means that they will overlap each other. But you also have the possibility to space them. So you can say cell 2 will be 5 meters from cell 1. So this is really useful if you are only interested to get data at a specific location in the water column.
Okay, great, Emily. There's one here that's who's asking for what connectivity for real time do we have?
You want to take this one, Stig?
What connectivity?
Yes, I guess the communication for the real time.
So the communication we have for real time, we have, of course, we can distribute over AIS. We can use different radios. We can use mobile, 2G, 3G, and also we have the possibility of using Iridium.
Mm-hmm. And because it's we are using the SeaGuardII, and the SeaGuardII has 2 serial ports, so you can easily connect any serial connection. So we have some standard solution we supply, but you can also use your own solution as long as it is serial.
Mm-hmm. Also, there is a question about self-clean.
Yeah. That would be great if it could be self-cleaning, but we haven't found any self-cleaning solution yet. I guess this refers to fouling problems. That's also one of the advantages using an instrument deployed further down in the water column, because there you have less light going in the water, so you have less fouling issues. But we use some anti-fouling paintings, or We have also been using UV lights, so it really depends on the application, on the amount of fouling.
And we also have testing going on at the moment for different fouling types, and trying to come up with better solution for that also, for especially when you look at some of the sensors, the water quality sensors.
Right.
Okay. I see that we're not going to be able to answer all the questions, and we're going to wrap up for now. Is there anything that you guys think that we should say before we?
Well, thank you for joining.
Yes, it's been a pleasure.
It's been a pleasure.
Absolutely.
Yeah. And if you have any questions, please feel free to contact any of us.
Yeah, and I think also we should say that there will be a recording available that we will send out latest tomorrow, and please feel free to share with anyone that you think would benefit from this webinar. And then I think what's left to say is that have a wonderful evening or day or wherever you are, and thank you very much for listening in. Okay.
Thank you very much.